Let me just welcome everyone. Today we have a talk by Team Adamo about amplitude and chiral fields in strong chiral backgrounds. So please start.
Okay, well, thank you. It's a great pleasure to be in virtual Moscow. Let's see if this is can you all see that? Is that working?
Yeah.
Yeah. Okay. 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 Good. So yeah. So today I'll tell you guys about some kind of recent and ongoing work that I've been doing in collaboration with a number of people, in particular with Lionel Mason and Atul Sharma, who are in Oxford. But also this builds on some work I've been doing also with Eduardo Casale, who's at UC Davis, Anton Ilderton, who's in Plymouth, and Stefan Nekovar, who was a research student in Oxford. I'd like to start by just kind of making some very general heuristic comments that many of you may have already heard before. And the first of these is about this general program, which kind of goes under the name of amplitudes or scattering amplitudes. And this is basically a program that's all about finding new ways to compute the S matrix, the perturbative S matrix of various quantum field theories, but in particular massless quantum field theories like Yang-Mills theory or general relativity. And I mean, of course, we're all familiar from our first quantum field theory class with some sort of traditional prescription for how to compute the S matrix. And the usual thing we do is use perturbation theory around a trivial background field configuration. We read off Feynman rules from the space-time Lagrangian. We draw all the diagrams that can contribute to a given process at a given perturbative order, and we compute. But over the last kind of 20 or so years, there's developed, I guess you could say, a kind of global research effort to try and find alternative recipes for computing scattering amplitudes that aren't coming directly from a space-time Lagrangian or Feynman rules. And there's been lots and lots of progress in this program, in particular for massless quantum field theories. And one of the hallmarks of this kind of new approach to scattering amplitudes is the presence of all multiplicity formulae. And what I mean by that is the ability to write down formulae that capture all tree-level scattering amplitudes of a theory for any number of external particles. For instance, and these all multiplicity formulae also exist in certain quantum field theories and under certain conditions beyond tree level, so at higher loops in the perturbative expansion. And these all multiplicity formulae, in general, there's just no way you could have ever arrived at them from standard space-time Feynman rules derived from a Lagrangian. So there's really something different going on here. But I think it's fair to say that there's not a common consensus about what that thing actually is. So in particular, you can ask yourself, are these new approaches to the computation of scattering amplitudes, are they just very interesting tools, or are they indicative of some new formulation or new formulations of perturbative quantum field theory in its own right, so to speak, or in their own right? So I just want to get us all on the same page by showing you some examples of these all multiplicity formulae that I mentioned on the last slide. So kind of one of the most famous ones of these for Yang-Mills theory is this thing called the Park-Taylor formula, which you may or may not have seen before. This captures all tree-level gluon scattering amplitudes in a particular helicity configuration in 4 dimensions. So this is an endpoint amplitude, so particularly the functional form of the amplitude scales with particle number, so there's no increase in complexity as you ramp up the number of external gluons. And you have some overall 4 momentum conserving delta function, and then you have a rational function of the kinematic data. If you've not seen these kind of angle bracket variables before, don't worry about it. They're essentially encoding the on-shell 4 momenta of the scattering, the gluons that are being scattered. And in this particular helicity configuration, it's called the MHV helicity configuration, 2 of the gluons have negative helicity, and the rest of them have positive helicity. So remember, in 4 dimensions, there are 2 on-shell polarization states for a gluon. And roughly speaking, you can think of those as having being decomposed into linearized self-dual or anti-self-dual gluons, or positive and negative helicity gluons. So that's what, in some sense, what this formula means. Like I say, if you don't parse the details. That the real thing to take away is that this is an endpoint formula that fits on one line, and it's not something you could ever have guessed just from the structure of the Feynman rules of the Yang-Mills Lagrangian. But in fact, we can do even better than just this one helicity configuration. We now know an all-multiplicity formula for the entire tree-level S matrix of Yang-Mills theory. So here, this is written as an expression for the tree-level S matrix of n equal 4 super Yang-Mills, but that supersymmetry is just trivial because this is a tree-level result, so you can always extract the pure gluon amplitudes from this just by doing some Grassmann integrals. And again, the point here is not for you to necessarily understand exactly what all the ingredients in this formula are. In some sense, we'll have a bit more to say about this later. It's more just to impress upon you the fact that it's possible to write entire tree-level S matrix of gauge theory, of Yang-Mills theory in 4 dimensions in this compact way in terms of moduli integral over the moduli of some holomorphic maps from the Riemann sphere. So these sigmas, these are marked points that live on a Riemann sphere, so something like CP1, into some complex projective variety, which we'll describe in more detail a bit later. So again, the point right now is not necessarily to understand this formula, just be amazed at such a thing even exists, because it's certainly not obvious from the perspective of the Feynman rules of Yang-Mills theory, or at least not obvious to me. And in fact, we can go do even better than this. We can go away from 4 dimensions and go to the tree-level S matrix of Yang-Mills theory in any number of dimensions. And this expression is, I guess, quite a famous one that was written down by Kachazo He and Yuan, going on 7 years ago now. And again, takes the form of some moduli integral that's localized on the support of some delta functions. The localization constraints are sometimes called the scattering equations. Not important to understand what that means right now. Again, this is not a formula that looks like it has anything to do with traditional space-time perturbation theory as we know and love it from our favorite Introduction to Quantum Field Theory class or textbook. So, okay, you can then ask,
Can I ask a couple of things?
Yeah, of course, please, please.
Yeah, so one question is concerning the S matrix for massless particles. So if you read old books, they all say that it's ill-defined.
Mm-hmm.
So is there any progress? So what's the current status?
So, okay, so, right, so there is, okay, so it's not well-defined because of infrared singularities, I guess, if that's what you mean. And in some sense, the S matrix, say, of n equal 4, let's talk about n equal 4 super Yang-Mills theory, because that's a theory where perturbation theory has a finite radius of convergence. In some sense, the S matrix is 1 for that theory. But that 1 emerges very non-trivially by, you have to exponentiate some IR divergences that emerge only at higher loop orders. Because these are tree-level expressions, they're perfectly well-defined. So that statement about the S matrix for a massless theory not existing, that's in some sense, that's a non-perturbative statement. It doesn't mean that you can't still define perturbative S matrix order by order, and that isn't a non-zero quantity. Now, okay, so that's one point. The other point is that there has been some progress on defining finite S matrices in massless quantum field theories by means of kind of doing a dressing of the asymptotic states. So there's work on this by Sao Tome and Akori, who are at or were in Michigan, and also by Matt Schwartz and one of his PhD students. I think the name is Hannesdottir. She's an Icelandic woman in Harvard. So there has been progress on that kind of non-perturbative question, but I'm not an expert on that by any means. Does that answer your question?
Yeah. And I also wanted to ask about this last formula. So it's somewhat implicit, right? And
good. Okay. So
I wonder to what extent, like, it's better than, let's say, just Feynman integrals encoded, like with that.
Yeah, that's a great question. So in some sense, the Park-Taylor formula is not implicit. But this RSVW, this Roybam-Spradlin-Volovich-Witten formula, is also sort of implicit Okay, it's very implicit the way that I've written it because I've not told you what any of the ingredients are. But there's also some set of delta functions that appears in these wave functions curly a that in some sense are equivalent to this set of delta functions here. So in some sense, the formula is implicit because there's an algebraic problem you have to solve in terms of localizing its integral on these delta functions. And that algebraic problem has some sort of factorial growth associated with it. So you could worry that it's no better than the factorial growth associated with Feynman diagrams. However, the factorial growth of this problem is bounded from above by the factorial growth associated with cubic Feynman diagrams. So it beats the factorial growth of ordinary Yang-Mills Lagrangian, maybe like 1 factorial order. That's still not very good. The key is that here, the factorially growing thing is an algebraic problem rather than a combinatorial one. So you know what all the constraints are. Whereas if you were summing Feynman diagrams, the point is that at each new order in multiplicity or in loop order, there's a whole new class of diagrams you have to draw that you don't know beforehand, or that you have to then draw, so to speak. Here you know exactly what the constraints are. So the growth in complexity is growth in complexity of an algebraic problem. And so there's analytic solvers for these equations now up to 6 or 7 points, I think, and numerical solvers to like very high numbers of points now. So if you want to literally get a number for the amplitude, so not a kind of nice algebraic expression, but you want to know a cross section or something, then there's still a sense in which this formula is superior to a Feynman one that's based on Feynman diagrams. But that's a really good point and one I probably should have made. Does that answer your question?
Yeah, okay, thank you.
Yep, no worries.
I may also have a very naive question. We know that at tree level, S matrix is essentially Lagrangian evaluated on stationary on solutions parameterized in a proper way. So in principle, it's not a miracle that at tree level there should be a compact formula for S matrix. It's just a matter of very non-trivial, non-local change of variables, which takes us from engaged fixings, right? Can you comment?
Okay, so that's another really good point. So and also provides a kind of good answer to Mitya's first question about how these things are defined. So yeah, at tree level, you can just think of the semi-classical S matrix, as you say, as the classical Lagrangian evaluated on some recursively constructed solution to the equation of motion, right? So I totally agree. I guess I would argue that if you wrote the S matrix in that form, if you said, okay, here's also an all multiplicity formula for the S matrix in that way, it would be much more implicit than these formulae, in the sense that you would, if I asked you at order 67, what is the precise form of the recursively constructed solution you have to evaluate the action on to get a 67-point tree level gluon amplitude, I think you would struggle to tell me what it was explicitly. Now you could argue, well, okay, you would struggle to tell me explicitly what the solution to these constraints was at 67 points as well. But even if you don't solve for these constraints explicitly, these formulae still manifest all the important properties of tree level scattering amplitudes, like factorization behavior, linear singularities, soft limits. They do all of that explicitly without any need to explicitly solve the constraints. That's a good point. I'm not really sure I've answered your question, but does that sort of inform what you were trying to ask?
No, to some extent, yes, thanks.
Okay, so I'm aware that it's not a complete answer. Yeah. Any other questions? Okay. So what I'd like to talk about today is about another kind of scattering problem that is sort of, in some sense, an obvious one, but one that we don't tend to learn about in kind of our introduction to quantum field theory textbooks, which is, what if we wanted to compute scattering amplitudes not around a trivial perturbative background, but against some non-trivial, or what's often called strong background. And so this question of scattering amplitudes in strong background fields, there are many reasons, many practical reasons to be interested in it. So These range from questions related to strong field QED in the realm of laser physics to high energy hadron scattering or effective field theories like the color glass condensate, gravitational waves, cosmology, of course, in some sense, the ADS CFT correspondence, and non-perturbative physics in general. But there's also good kind of esoteric reasons to be interested in scattering amplitudes on strong backgrounds, which is that there's a huge knowledge gap between what we know about scattering amplitudes on a trivial background and what we know about scattering amplitudes in even the simplest strong background fields. So and even the simplest of these strong backgrounds at tree level for Yang-Mills theory and general relativity, as far as I know, the best formulae that anyone had computed until this year, for instance, were 4-point formulae. Okay, you should compare that against the formulae I showed you on the other page, which were all multiplicity formulae for the entire tree level S matrix, again, around a trivial background. So it seems that even if you turn on the most simple or highly symmetric, for instance, but non-trivial background fields, kind of everything breaks down. The problem just becomes super, super hard. And from a Feynman rules perspective, that's not surprising, right? Because the Feynman rules become very complicated on non-trivial background fields. You may even struggle to write them down explicitly in a way that you can actually compute anything with. But okay, if our friends in the amplitudes community, or our most ambitious, most vocal friends in the amplitude community are to be believed, all this progress that's happened over the last 20 years, that's supposed to be the harbinger of some new reformulation of quantum field theory. And if that's true, then we should see that in any background that we want to compute in, not just a trivial one. And if we do only see it in a trivial one, then all of those beautiful advances, they're still beautiful and they're still advances, but they're really advances about the amount of symmetry that you have in a trivial perturbative background, not something deep about quantum field theory, I would argue. So today, the basic question I want to ask is it possible to make all multiplicity statements about scattering amplitudes in strong background fields? And the strategy is going to be to consider a very particular class of strong background fields, but one which is still fairly general. And by fairly general, I mean it encodes, the background field has functional degrees of freedom. So it's like an uncountably infinite class of strong backgrounds. And the ones we're going to be talking about are 4-dimensional, chiral, source-free, and asymptotically flat. So they're kind of complex backgrounds. But they're ones that are suitable for setting up a scattering problem on. Okay, so that's the aim of the game, is to try and see, can we make all multiplicity statements about scattering amplitudes in Yang-Mills theory or general relativity on any strong background, and in particular, we're going to consider these particular chiral source-free backgrounds. So let me start with something which might seem like a bit of a digression, which is a kind of review of the conformal compactification of Minkowski space, but in a slightly different language than some of us might be used to. So I'm sure many of us have heard that you can conformally compactify Minkowski space, and that means kind of rescaling the metric by conformal factors such that infinity becomes a finite hypersurface in the conformally rescaled spacetime. Now, the null boundary of that conformally rescaled spacetime is called scry, and it decomposes into a future null infinity and a past null infinity, and each of these have the topology of a light cone. You can think of past null infinity as the future light cone of past time-like infinity, and future null infinity as the past light cone of future time-like infinity. And usually these things are charted with what are called Bondi coordinates, but there's kind of a beautiful projective way of thinking about them as well. So if scry plus or minus has the topology of a light cone, that means it's like R cross S2, but we can always identify S2 with the Riemann sphere, CP1, and then we can describe it using homogeneous coordinates. So let me call those homogeneous coordinates on CP1 lambda and lambda bar. So they're homogeneous coordinates on a one-dimensional complex projective space, which means I need 2 of them. So I organize them into an SL2 spinor pair and its complex conjugate. Complex conjugation interchanges SL2 spinor representations. So I have an undotted index for my holomorphic homogeneous coordinates and a dotted index for my anti-holomorphic homogeneous coordinates. And then I have another coordinate u, which is the coordinate on the r factor of scri plus or minus. So the coordinate up and down the generators of scri, if you like. And these are homogeneous coordinates in the sense that I identify them up to overall projective rescaling. So rescalings by a non-vanishing complex number. And identification is that if I scale lambda by a, where a is a non-vanishing complex number, and lambda bar by its complex conjugate, this coordinate u up the fibers scales as mod squared of a. And that's actually dictated by the Lorentz group. So we want this coordinate representation to preserve Lorentz invariance. So that's one advantage this has over the usual kind of Bondi coordinate chart, is that this doesn't break Lorentz invariance. But for that to be true, u needs to scale as mod squared of a whenever we do one of these projective rescalings. But then the conformal class of degenerate metrics on this null hypersurface scri, say scri plus for instance, is 0 times du squared plus conformal metric on the 2 sphere, which is just proportional to holomorphic one form on CP1 of weight 2. So this angle bracket notation denotes contraction on SL2 spinor indices, undotted SL2 spinor indices. And that means we raise and lower SL2 spinor indices using the 2-dimensional Levi-Civita tensor, the canonical invariant tensor under SL2. And d lambda bar, big D lambda bar is just the complex conjugate of this. And what this means is that you can view scri plus as the total space of line bundle, a real line bundle over CP1. And that's just the line bundle of real functions that scale as weight 1 in the holomorphic homogeneous coordinate and 1 in the anti-holomorphic homogeneous coordinate. So these words here are another way of saying this projective identification under rescalings relation up here. So this might look like something scary, but it really isn't. It's just a way of giving coordinates to a light cone, a null hypersurface with a degenerate metric, such that you don't break Lorentz invariance. So there's some natural line bundles that live over scri in this language, and these are just the line bundles of functions that are homogeneous of weight p under weight p and a under this rescaling, and weight q and a bar under this rescaling. So these are just completely natural things to describe in these coordinates. And the reason why we like these line bundles is that they encode the normal notion of spin and conformal weight, which are familiar from functions on the sphere, or more generally, but in this particular case, functions on scri. So the spin weight of an object on scri, that corresponds to the difference in its holomorphic and anti-holomorphic weights in this projective description, and the conformal weight is encoded in the sum of the holomorphic and anti-holomorphic weights. Okay, so this goes way back to work in the 80s by George Sparling and Mike Eastwood and Paul Todd. It's not a very widely used description of scri, but I think it's quite a nice one. So the reason why I told you about that is that this homogeneous geometry of scri gives a good way of characterizing the kind of background fields I'd like to talk about. So in 4 dimensions, an asymptotically flat gauge field in temporal gauge at scri, so in the conformally rescaled spacetime, it looks like sum of 2 terms where there's a free Lie algebra valued function it's proportional to a holomorphic one form on the S2 factor of scri and its complex conjugate. And this object curly A naught, it takes values in one of these line bundles. So it has weight -2 under a holomorphic rescaling and weight 0 under anti-holomorphic rescaling. And its complex conjugate, you just flop the weights, right? And these objects define what's sometimes called the broadcasting function of the gauge field. It's just taking a u derivative, so a retarded time derivative of this function curly A. So remember, u has weight 1, 1 under a projective rescaling. So if I take a derivative with respect to u, that needs to kick both weights down. So the broadcasting, the holomorphic broadcasting function, if you like, has weight -3, -1, and is valued in the Lie algebra of the gauge group. And okay, so why am I telling you all about this? Well, I'm going to define what I mean by a radiative gauge field as being an asymptotically flat gauge field, which is uniquely characterized by this broadcasting function. In particular, that means that there's some sort of Kirchhoff-Hadamard formula, type formula, that treats this object as initial data, which defines the gauge field everywhere in space-time, in the, if you like, in the bulk of the space-time, away from infinity. Usually one assumes that this broadcasting function is smooth everywhere, but in fact you can relax that assumption and allow it to be smooth everywhere except on isolated generators of scry, and that allows you to include plane waves as a special case of this radiative class of gauge fields. So you can also show that this condition, that a gauge field is uniquely characterized by its broadcasting function, it rules out anything with a source, basically, or anything that has lower multiple, like monopole moments. So something like a Coulomb field would not be a radiative gauge field. But the example you should always have in the back of your head is plane waves. Plane waves are radiative. Now, we've restricted our attention to 4 dimensions, and what that means is that the field strength of any gauge field can be decomposed into its self-dual and anti-self-dual parts, because the space of 2 forms in 4 dimensions is involutive under the Hodge star. And all that means is that if I take the Hodge star, the anti-self-dual part, I get -I times the anti. These self-dual and anti-self-dual parts are controlled by broadcasting functions, as you might have expected. So the self-dual part is controlled by U derivative of curly A bar, and the anti-self-dual part is controlled by the U derivative of curly A. Now, in a Lorentzian, for a Lorentzian real gauge field, this curly A and curly A bar, they really are complex conjugates of each other. So they're, if you like, the self-dual and anti-self-dual part of the gauge field are related by complex conjugation. But if we allow ourselves to consider complex gauge fields, then curly A bar becomes a completely independent quantity, which I'll call curly A twiddle. And what that means is that the anti-self-dual part of the gauge field is no longer equal to the self-dual part's complex conjugate. They're independent degrees of freedom. Another way of thinking about this is that you could go to Euclidean signature instead of Lorentzian signature. There, the self-dual and anti-self-dual parts are independent quantities as well. But we want to talk about a scattering problem, so it's best to stay in Lorentzian signature, I think. Okay, so then the definition of the kind of background fields we're going to be working with is self-dual radiative gauge fields, and those are radiative gauge fields which are complex, are characterized by their curly A naught being 0 and the curly A twiddle being non-zero. In other words, we kill half the curvature of the gauge field, we kill the anti-self-dual part, we leave the self-dual part free. And it's freely specified by curly A twiddle naught. Okay, so that's just a definition. So just to sum up everything that, if you kind of zoned out in those last few slides, here's the roundup. Self-dual radiative gauge fields, these are complex or chiral 4-dimensional gauge fields. They're purely radiative and source-free. They're characterized by free asymptotic data in the form of this broadcasting function, or a U derivative of their kind of leading asymptotic component, this curly A twiddle. They're asymptotically flat by definition, which means the S matrix is going to be a natural observable on this background. And they include plane waves or superposition of plane waves as an example. So if you like thinking about impulsive plane waves as the kind of prototype of every strong background field, then those are included in this class. Self-dual plane waves are included in this class of radiative gauge fields, self-dual radiative gauge fields. Now, I've told you a story here that's all about gauge theory, but there's a virtually identical story for gravity, where the thing you wind up with is this notion of self-dual radiative spacetimes. These are complex solutions to the vacuum Einstein equation, have purely self-dual conformal curvature, and are specified by one free function at scri. Okay, so the key takeaway here is there's functional freedom in these backgrounds corresponding to this curly A twiddle. Okay. So the question, to reiterate, is can we compute gluon scattering amplitudes on one of these self-dual radiative background gauge fields? So from the perspective of traditional approaches to quantum field theory and strong backgrounds, you'd say this seems really hard, maybe even impossible, because the background has functional degrees of freedom. You're not going to be able to write down explicit Feynman rules.
Can I ask a question?
Yes, please, please.
So if you mean some applications, yeah. So from the very beginning, can you say that if this technique can be used for the instanton, for example, which is kind of
great question. Let me say, I'll return to this at the end,
okay.
this question at the end.
Okay.
Instantons are not in this class of self-dual radiative backgrounds. Because if you like, the instanton has a center, and somehow that is like a source in some sense. So no, instantons aren't in this class. Or if you like, the instantons that are in this class are topologically trivial. So they're maybe not the kind of most interesting ones I think that you have in mind, but I'm optimistic that the general formalism that I'm going to describe to you now can be applied to instantons, but they are not in this class. Yeah, sorry. That's a good question. Does it make sense what I've said?
Yeah, I understand. Yeah.
Okay, thanks. Okay, so yeah, so this seems like a really hard problem, kind of thinking about things from a traditional perspective. And they're also, I mean, even if you ignore this fact that, like, how are you going to write down explicit background coupled Feynman rules with these functional degrees of freedom? Even if you ignore that for a second, there's also just many new subtleties in the game now. As soon as you turn on non-trivial background fields versus what we're used to in trivial background. So there's no momentum conservation. From the perspective of space-time Feynman rules, there's always going to be position space integrals left over in the game because you have these free functions in the game that will obstruct doing Fourier integrals the way that you were used to doing them in a trivial background. There's also this concept of the memory effect, which is that if you take a gluon that looks like a momentum eigenstate, e to the I k dot x at scri minus, and you throw it into one of these backgrounds, even though the background is asymptotically flat, so when it comes out at scri plus on the other side, it looks like a trivial vacuum there. The gluon remembers the fact that it's crossed a radiation field, and it no longer looks like e to the I k dot x at future null infinity. So that's something that goes under the name of the memory effect and is quite a fashionable thing to think about nowadays for many other reasons. But that's a simple way of thinking about the memory effect. You take a particle, you throw it through a radiation field, and its wave profile has completely changed when it comes out the other side. Even though it solves the same free field equation asymptotically, it no longer looks like a pure momentum eigenstate. And that's just the fact that it's interacted with the radiation as it's gone through. There's also something called tail effects, which will emerge, which basically mean that gluons in a scattering process will interact with each other as usual, as we're used to from a trivial scattering background, but they will also interact with the background itself. And these background interactions will contribute directly, make direct contributions to a generic scattering amplitude. So it just, this seems like a difficult problem, one that might be hard to tackle. But there are some hints that actually we might have an angle for getting after this. So the first is to take your usual Yang-Mills action, so that's the first term here, and shift it by auspiciously chosen multiple of the topological term. So trace f wedge f. This is like a Chern class, so it's a topological term, which means it doesn't affect perturbation theory. So even though as non-perturbative quantum field theories, first term and then first term plus the second term are certainly different objects. From a perturbative perspective, in asymptotically flat situations, these those two semi-classical field theories will have the exact same perturbative observables. So in particular, their tree-level S matrices will coincide. Doesn't care that you've added this multiple of the topological term. That multiple of the topological term miraculously means that the action you wind up with only depends on the anti-self-dual curvature of F. So I'll leave it as an exercise to the reader to show that with this appropriately chosen multiple, this is what you wind up with. It's just something proportional to trace F minus wedge F minus. And so why is that an interesting thing to do? Well, you can write trace F minus wedge F minus in an interesting way by introducing a Lagrange multiplier. So let's take some two form, some anti-self-dual two form B with values in the Lie algebra of the gauge group. Then it's easy to see that you can write this action trace F minus wedge F minus as trace F minus wedge B plus G squared trace B wedge B. So I'm really, really sorry. My wife is calling me and she's at the doctor's with our son. So if you just give me 1 second, I just need to answer the phone really quick. Sorry. Hello? I got the times wrong, so I'm actually giving the seminar right now. Okay, bye. Bye. Okay, sorry about that, guys. All right, let's see. Are we back in action? Can everyone see this again?
Well, actually, no. Oh, no, yes. Yeah, now it's fine.
Yeah, is it okay? Okay, cool. Thanks. Okay, so sorry. So we introduced this Lagrange multiplier, and that means that this trace F wedge F minus wedge F minus, we can write that as a term that's F minus wedge B plus a term proportional to the coupling constant squared B wedge B. And again, you might ask why. This is just some trivial rewriting of things. The point is that the field equations of this Lagrangian take an interesting form. Tell us that this anti-self-dual 2 form B solves the zero rest mass equation, where D is the covariant derivative associated with the gauge potential A, that the anti-self-dual curvature of that gauge potential is equal to, well, minus the coupling constant squared times that anti-self-dual 2 form B. What does that mean in real money? It means that Yang-Mills theory admits a perturbative expansion around the self-dual sector, right? Because when I set the coupling equal to 0, that gives me F minus equals 0, which is the equation for self-duality. So it says by doing this shift of the Yang-Mills action by a topological term, I get a new theory, or I get a theory rewritten in a way such that the small coupling expansion is an expansion around the self-dual sector. So that's something that, at least as far as I know, was first observed by Chalmers and Siegel a long time ago, back in the 90s, I guess. But one very optimistic way of interpreting that that statement is that perturbatively expanding around self-dual radiative background should be no worse in some vague hand-wavy sense than perturbatively expanding around a trivial background. They both correspond to small coupling expansions of the Yang-Mills action, or actions that are perturbatively equivalent to Yang-Mills theory. Now, what we need is some tool that manifests this triviality of the self-dual background. Okay, so luckily, such a tool exists. So I'm now going to give you the quickest introduction to something called Twistor theory that you'll ever see. So obviously it will be incomplete in some sense, but hopefully will impart sufficient amount of information for our purposes today. So Twistor space, this is, we're going to call this PT, and it's an open subset of CP3, the three-dimensional complex projective space. Three-dimensional complex projective space I can describe with 4 homogeneous coordinates. We call those homogeneous coordinates ZA, and I split them into two SL2 spinors of opposite chirality, mu alpha dot and lambda alpha. The open subset I'm going to choose to work with is the subset where the lambda alphas are not all vanishing.
Tim?
Yes?
Sorry. Could you remind me, is there any connection, moral connection, to Rossley-Selivanov?
Absolutely. Yeah, there absolutely is, and we will come to this. Yeah, we'll come to this.
Okay, thank you.
Yeah, great question. Yeah, so at this point, not yet, but there will be, and it's in some sense it is related. Yeah, good question. Okay, so the whole machinery of Twistor theory derives from a non-local correspondence between this complex projective variety PT and Minkowski space, or complexified Minkowski space. So this X could be an R13 so Minkowski space, but we'll just complexify everything and talk about C4 for the time being. The correspondence is that a point in Minkowski space corresponds to a linearly embedded holomorphic Riemann sphere in Twistor space, which we call big X. And these things are often referred to as Twistor lines. That correspondence is encoded by something called the incidence relations. And this is just an algebraic identity that relates X to mu and lambda, the two parts of the homogeneous coordinates on Twistor space. And hopefully you don't have to look very long at this equation to convince yourself that this is the equation for a linearly embedded holomorphic Riemann sphere in CP3. And Twistor theory is a very useful object in the study of scattering amplitudes on a trivial perturbative background. Know that massless free fields are encoded in cohomology on Twistor space, so in particular things like gluon wave functions. It gives a nice representation for on-shell scattering kinematics, and I showed you a formula on like the second or third slide or something for the full tree-level S matrix of n equal 4 super Yang-Mills in a trivial perturbative background. That formula is based intrinsically on this Twistor correspondence, and there's also an analogous formula for gravity or for supergravity, which I didn't show you. So we already know that this is a useful tool in the study of the scattering amplitudes of Yang-Mills theory, at least tree-level scattering amplitudes of Yang-Mills theory in a flat background. Now we can ask what this has to do with perturbation theory on a self-dual background. And the reason why this is something interesting is all due to a really important theorem, beautiful theorem of Richard Ward from 1977, which tells us that there's a one-to-one correspondence between self-dual solutions of the Yang-Mills equations on complexified Minkowski space, or on Minkowski space if you add some reality conditions, and holomorphic vector bundles on Twistor space, which are trivial when they're restricted, topologically trivial when restricted each Twistor line. And then if you want to pick out a particular gauge group, so for instance, SUN, you have to add some additional technical assumptions about this vector bundle. So for instance, for SUN, it needs to have trivial determinant bundle and needs to admit a positive definite real form. So that's like giving you a killing form and making it SUN instead of UN, basically. So anyway, we won't be too concerned about those technical conditions. The punchline is that Twistor theory in some sense trivializes the self-dual sector by rewriting it in terms of holomorphic data on Twistor space. Okay. I'm really sorry. I need to stop for just 1 second, and I'll be back. I just need to help my wife really quick. Sorry, this will just take 1 minute. Okay, sorry, back and better than ever. All right, let's try this one more time. Hopefully, will be our last interruption. I'm really sorry about this. It's very unprofessional. Okay, are we back and everyone can see that?
Yeah.
Okay, thanks very much. All right, so we have this theorem of Ward, which tells us that the self-dual sector of Yang-Mills theory is equivalent to a holomorphic structure on some vector bundle in Twistor space. And the punchline is that that actually is going to allow us to trivialize these self-dual backgrounds in a precise way. So what do I mean by that? The self-dual sector is encoded by holomorphic vector bundles. Another way of saying that is that we can write a partial connection, so a deformed complex structure on these vector bundles. Locally, such a thing will always look like a deformed D-bar operator or a deformed T-holomorphic Dolbeau operator. So that's something that looks like their Dolbeau operator plus a kind of connection not one form. So this A is something valued in the endomorphisms of this Ward bundle E, and it's a not one form. This differential operator has to be integrable. It has to square to 0. So that's the holomorphicity condition from Ward's theorem. And it turns out that for the class of fields that we're interested in, these self-dual radiative fields, you can write down what this partial connection is explicitly. So it's just proportional to that function, the functional degree of freedom in the background itself, at early A twiddle, kind of pulled back to Twistor space, and then proportional to some not one form component. So this was worked out again a long time ago in the 80s by Sparling, Newman, Eastwood, and Todd. So these self-dual radiative gauge fields, there's something that can be described extremely naturally in terms of Twistor theory, in terms of an integrable complex structure, where we have a very explicit realization of what the complex structure actually is in a particular gauge choice, if you like. Okay, now all those technical assumptions in the Ward theorem, which I didn't really linger on too much, they have an interesting consequence, which is that if I look at this kind of holomorphic bundle on Twistor space, and I look at it restricted to any Twistor line, so that is restricted to any linearly embedded holomorphic Riemann sphere inside my Twistor space, it means that there exists a holomorphic trivialization of the bundle over that Riemann sphere. What that means in real money is that we can find a frame H, so this H depends on which line we're over and also where we are along the line, such that if I hit H with this kind of partial connection restricted to the line, I get 0. So if you like, that's a definition of what a holomorphic trivialization is. But this frame, this holomorphic frame H, is the thing that encodes the space-time degrees of freedom of the gauge field. So in particular, if you form this combination of H's inverse and then hit that against a differential operator lambda alpha and then a space-time derivative, so this is d by dx alpha alpha dot, so alpha alpha dot x alpha alpha dot, those are the coordinates on Minkowski space, and have that operating on another copy of H. Liouville's theorem essentially tells you that that has to be proportional to the lambda alpha contracted into some object that only depends on x. And this object will be valued in the Lie algebra of the gauge group, have indices alpha alpha dot. So that object we can treat as a gauge potential. And furthermore, you can show that integrability of the partial connection, the fact that d bar squared is equal to 0, imposes this gauge potential has a field strength which is self-dual. So in other words, the holomorphic frames H, these are the things that encode the background, encode the gauge, the self-dual radiative gauge field on space-time. They're the things that encode it up in Twistor space, these holomorphic trivializations. If I had a flat gauge field, so a trivial gauge field, then this frame would just be the identity matrix. Okay, so that's maybe a bit abstract, but if we look at a particular example where the self-dual radiative gauge field is Cartan-valued, so it takes values in some Cartan subalgebra of the Lie algebra of the gauge group, then these holomorphic frames are just exponentials, where the exponential is the exponential map of the gauge group. And this Lie algebra valued function G is something you can determine explicitly in terms of an integral formula from the free radiative data of the self-dual radiative gauge field. So remember, if someone says, okay, here's my favorite self-dual radiative gauge field, what that means is that they've given you curly A twiddle. And what this is saying is that you can then construct the holomorphic frame on Twistor space explicitly by means of an integral formula. So here you do an integral over one copy of CP1 in terms of the line X on Twistor space. And remember these angle brackets, those correspond to SL2C spinor contractions. There's this funny spinor O that appears, and you might wonder, well, geez, that looks like I'm introducing some new dependence in my formula. In fact, the choice of O is just the choice of gauge for the space-time gauge field. And a way of seeing that is that you can read off space-time gauge potential from the broadcasting function in this way, and you see the spinor O appears there. You can show that changes in O just correspond to gauge transformations of the space-time gauge potential. So anyway, takeaway from that is that self-dual radiative gauge fields are encoded on Twistor space in terms of these holomorphic frames. So that's how we encode the background. What about gluon perturbations? Well, those are encoded by cohomology on Twistor space. So in particular, positive helicity gluons are given by homogeneous 0-1 forms that are annihilated by this partial connection big D bar, are not big D bar exact, and take values in endomorphisms of the bundle. Negative helicity gluons, same thing, except they're a different homogeneity weight. Homogeneity weight is -4 on Twistor space. And we can be very explicit about what these homological representatives are. If we want our asymptotic gluons to have, say, before they cross the self-dual radiative background, to have on-shell momentum K alpha alpha dot. It's on-shell, which means it's massless, which means it can be decomposed into an undotted and a dotted two spinners, vial spinners. Then we can be very explicit about what these gluon eigenstates look like on Twistor space. It's not terribly important that you absorb what exactly all of this means, but I just want to convince you that this is not some esoteric exercise. We can be very explicit about what the gluon wave functions look like on Twistor space. Now we want to use all of this to actually compute something. So the idea is to start out on space-time, and that Chalmers-Siegel Lagrangian that we wrote down earlier, it gives for us a generating functional for all the MHV amplitudes of Yang-Mills theory in 4 dimensions. So remember, an MHV amplitude has 2 negative helicity external gluons and the rest positive helicity. And so the generating functional is just given by the second term in that Chalmers-Siegel Lagrangian. I've here normalized it by some powers of the coupling. That's not important. It's just trace B alpha beta, B alpha beta. So B alpha beta, those are like the components of an anti-self-dual 2 form in 4 dimensions. And this B alpha beta depends implicitly on a background gauge potential because it satisfies a PDE, and that PDE encodes a self-dual gauge connection because this is a covariant derivative. And the idea is that the positive helicity gluons in an MHV amplitude are encoded by perturbatively expanding this functional in the self-dual gauge connection background that enters implicitly through these B's and the fact that they're on shell. And so this is something that was spelled out, I guess, by Mason and Skinner back in 2008. The key idea is that we want to take this self-dual gauge connection in this generating functional, write it as a piece that's a fixed, non-perturbative, self-dual radiative background, and then a piece that's composed of a bunch of positive helicity gluons propagating on that background. Now, doing that is really difficult on space-time. In fact, I don't know of any kind of successful calculation does that on space-time, but it's actually easy on Twistor space because everything in Twistor space is just boiled down to these holomorphic frames. So that generating functional I wrote here, you can lift it to Twistor space using the Twistor correspondence. It takes this form. So you have an integral over space-time, which in Twistor language corresponds to an integral over the moduli space of these Twistor lines, these degree-1 holomorphic curves in Twistor space. And then you have some bit that's given by a bilocal integral over 2 copies of one of these Twistor lines. You have 2 negative helicity gluon wave functions, and then they're conjugated by these holomorphic frames. And the hats on the holomorphic frames, oh, sorry, there should be hats here, my fault. The hats on the holomorphic frames, they tell us that these are the holomorphic frames associated to a partial connection that includes the background self-dual radiative gauge field, and then some arbitrary number of positive helicity gluon perturbations to it as well. And the idea is we want to perturbatively expand this generating functional, the little ai's, while keeping the big A fixed. So that's our kind of non-perturbative background. Now, you can do that by expanding conjugations of these holomorphic frames as a Born series in the little ai's. That's okay, a straightforward exercise. You get some formula that looks like this. I don't want to bore you too much with the details of unpacking it. The upshot is that it gives you straightforwardly an expression for the endpoint MHV amplitude on a self-dual radiative background. Here I've written this in n=4 supersymmetry language just to make it a bit more of a homogeneous expression. It's easy to write it for pure Yang-Mills as well. We just get an integral, one integral over space-time position, an integral over n copies of CP1 trace, and then an ordered product of these Twistor wave functions for the external gluons conjugated by the holomorphic frame. So that holomorphic frame is encoding the fact that we're on a non-trivial self-dual radiative background, then normalized by some spinor contractions. So this denominator is sometimes called a Park-Taylor denominator, but this is a denominator that lives on CP1, not momentum space in the first instance. Okay, so here we go. This is an all multiplicity formula for scattering on a non-trivial background field, tree level scattering, MHV scattering on a self-dual radiative background field. Now, you might say that looked like a pretty abstract formula. What are these holomorphic frames doing? It turns out if you take specific examples, so the example we gave earlier was of a Cartan-valued background, you can be very explicit about what the formula is. So you can do all of the CP1 integrals and really boil it down to a momentum space expression. Get usual Park-Taylor factor that I showed you at the very beginning of the talk in front. Instead of a momentum conserving delta function, you're left over with a single position space integral, where these EIs, these are charges of the individual gluons with respect to the Cartan-valued background. There's some charge conservation that's implicit here as well. This Cartan-valued function G, this is the thing that defines the holomorphic frame and is in turn defined by the free radiative data of the self-dual radiative background. So there's even further simplification of this formula if you restrict to the special case of plane waves. There, it turns out that 3 of these position space integrals can be done analytically, and there's only one of residual integral left over. So the fact that we derived this from first principles from a space-time generating functional in some sense kind of proves that the formula is correct, but there's one red flag, which is that there's a single position space integral in this formula for arbitrary multiplicity. You would expect there to be at least 4 into n-2 such position space integrals for an endpoint tree amplitude coming from just the Lagrangian of Yang-Mills theory in a background field. So what's going on? It looks like this formula is way too simple. This gets back to a comment that Arkady had a few minutes ago, which was that it turns out you can do a non-local field redefinition of the Yang-Mills action that recasts it in a way that all MHV amplitudes come from a single contact contribution. And so that's work by Rosley and Selivanov and also by Paul Mansfield. So in some sense, that's the explanation for the simplicity here. Although arguments that these people had, as far as I know, there's no way you could use them to actually derive that formula I had on the previous page. Just what you could use them to is to derive the expectation that you would get a formula with only a single position integral left to do. But the rest of the formula you'd never be able to derive that way. But anyway, this is the resolution for why you have so few integrals. There's some highly non-trivial field redefinition you could do that recasts the action in such a way. Also, there are other sanity checks you can do to that formula. You can, we've checked it explicitly against background perturbation theory at 3 and 4 points. You can take its perturbative limit, which is where you think of the self-dual radiative background as a single gluon, and then see that you recover the n+1 point MHV amplitude on a flat background. Also, it has the correct flat background limit. If you turn the background off, you just recover the Park-Taylor formula, including its momentum-conserving delta functions. Okay, so I'm conscious of having gone over time due to my lack of organization here, so I'll try to wrap up as quickly as possible. The last thing I want to tell you is that it's easy now to write down a conjecture for the full tree-level S matrix on one of these self-dual radiative backgrounds. You do that by just kind of bootstrapping that MHV formula up to arbitrary degree curves rather than just linearly embedded CP1s. And that's an idea that goes back to Witten and this, I guess, set of concepts that are often called Twistor string theories. But anyway, here that formula for the complete tree level S matrix for an n to the k MHV amplitude. So this is an amplitude with k plus 2 negative helicity external gluons and the rest positive helicity. This formula only has 4 into k plus 1 integrals, which beats your expectation from space-time perturbation theory in every helicity configuration. So this formula for k greater than 0 is a conjecture. It passes many non-trivial sanity tests like perturbative limit, checks against low point computations in explicit Feynman diagram calculations, and flat space limit. You can also derive it from Twistor string theory, which I think is a pretty powerful check as well. So anyway, I'll wrap up now. The upshot to take away from this is that it is possible to make all multiplicity statements in strong backgrounds. There's another version of this story, which I didn't tell you, for gravity in self-dual radiative spacetimes. It's just a bit more complicated, but otherwise very much the same. But there are many kind of exciting things, I think, to work on here. One obvious one is to try and prove that n to the k MHV conjecture I showed you on the previous slide here. It also turns out that you might worry that, okay, this is a bit of an esoteric playground because these backgrounds are complex, and surely we should be interested in real backgrounds for actual pheno applications. But it turns out that chiral backgrounds provide a model for certain back reaction phenomena in strong field QED and QCD, things that are sometimes called beam depletion. There's also, since we now have conjectural formulae for the entire tree level S matrix of gauge theory and of gravity on these self-dual radiative backgrounds, it raises the question if there's some notion of double copy between them. That's actually quite a difficult question, it turns out. Obviously, something we want to do is generalize away from these chiral radiative backgrounds to just generic non-chiral radiative backgrounds. Is it possible to get all multiplicity statements there? And also coming back to a question that was asked earlier, is it possible to do other self-dual backgrounds with this formalism which aren't radiative? So for instance, instantons, which was mentioned, or dions, things that kind of have a source or some interesting topology. I think the answer is yes, but I don't have any beautiful formulae to show you yet. It's something we're thinking about. So in any case, thanks very much for your time, and sorry for the lack of organization on my part.
Thank you very much. Are there any questions?
Can I ask something? Hi, Tim. So what is the main obstruction to generalizing all these formulas to general strong backgrounds? So what goes wrong? You have this nice theorem of Ward and so on, but so why can't you get most general backgrounds right away?
That's a great question. So the intuitive reason is that the thing that's running the show here is Twistor theory, and Twistor theory is an intrinsically chiral formalism. It picks a handedness, if you like, and then does everything in terms of perturbations away from that handedness. And so in the set of conventions I've chosen here, the handedness is the positive helicity or self-dual sector. And so Twistor theory has a very hard time giving nonlinear, non-perturbative descriptions of things that are not self-dual, purely self-dual. This is something that if you ask Twistor theorists from the 80s or earlier, it's something they called the googly problem. This is apparently a cricket reference, so it's like the most British thing ever. But like what it means is that it's just not known how to encode generic nonlinear curvatures in Twistor theory. So that's the big obstruction with the formalism that I've shown you here. What you can do is pick a generic self-dual structure and then perturb away from it in any direction. That's what we've done here. But picking your nonlinear, non-perturbative background to have generic curvatures seems quite difficult in this formalism. However, there's another Twistor-like formalism, which is called ambi-Twistor theory, which is maybe a slightly misleading name, but that is not a chiral formalism. And the hope, my hope at least, is that it will be possible to tell a version of this story that is in some sense analogous to the story that I just told you in that ambi-Twistor formalism for a generic background that isn't just chiral. But it turns out there's all sorts of subtleties in that formalism that don't appear in this one. So I think it's a hope that it's going to be possible, but yeah, we certainly haven't achieved it yet. Does that answer your question, Jenny?
Yeah, many thanks. Then self-dual part of my question, why can't you consider all self-dual backgrounds right away?
Good. So you can. So Twistor theory, that theorem of Ward, there's nothing in that theorem about radiative. None of these radiative words that I told you about beforehand appeared in that theorem. So Ward's theorem captures every self-dual background. The thing that's special about the self-dual radiative backgrounds is that it's very easy to describe the gluon perturbations around those backgrounds. And the reason for that, so it's a technical reason, but I think one that it's sort of easy to explain. So let me try and explain it. The partial connection on Twistor space, this big D bar operator, that's the thing that runs the show. The non-trivial part of it is only proportional to D lambda bar. Okay, that means that any not one form on Twistor space, which is proportional to D lambda bar, will automatically be closed with respect to the deformed complex structure because D lambda bar wedge D lambda bar is 0 because it's a one form. Right? What that means is that we can use these very simple momentum eigenstates, which are actually the same as the momentum eigenstates you use on a flat or a trivial background. That's because the D bar, their anti-holomorphic form component, is only proportional to D lambda bar. They're kind of trivially homology classes in the deformed complex structure for the Twistor space, even though they're also homology classes in the flat complex structure. So that's the thing that makes these self-dual radiative backgrounds really easy to work with. On a generic background like an instanton, for instance, or a dion or something more complicated, the background partial connection will have terms in it that are proportional to D lambda bar and D mu bar. And that means you have to think a lot harder about what your cohomological representatives for the external scattering states will be. It doesn't mean it's impossible. It just means that you need to have some new ideas, which we didn't need to have to do this story. So sorry, it's a bit of a technical answer to your question, but hopefully it makes some sense.
Yeah, many thanks.
No, it's a pleasure.
Excuse me, still, can you better explain what is wrong with instantons, say, in the pure Young-Mills?
Yeah, absolutely. So I want to emphasize, there's nothing wrong with them. It's just we haven't figured out all the details of doing this story there. So the obstruction is precisely this thing I was just telling Eugenia about. So the background complex structure, so any self-dual gauge field is described on Twistor space by some deformed complex structure, big D bar, right? And that big D bar locally can be written as a kind of flat D bar plus some, if you like, connection one form A. And for an instanton, that connection one form, it's a not one form, it has form components proportional to D lambda and D lambda bar. sorry, d lambda bar and d mu bar. And what that means is that it's much more, there's a non-trivial PDE you have to solve to write down explicit cohomological representatives that are in the cohomology of that deformed d bar operator. That's really the obstruction, basically. So it's not an obstruction. It just means you have to, there's a harder problem you have to solve. Whereas for these self-dual radiative backgrounds, you can take the same cohomological data that you used on a trivial background.
That's the thing I don't understand, because instanton is a self-dual solution, right?
Mm-hmm.
So probably my question is, well, you are saying that you oppose the instanton to the generic self-dual background. That's why I am confused. So
no. So yeah, sorry. I think maybe I'm failing to make to be sufficiently clear. I absolutely agree. Instantons are self-dual, can be thought of as self-dual backgrounds, 100%. But they cannot be thought of as self-dual radiative backgrounds. So in particular, they are not uniquely characterized by this object that I called the broadcasting function in this talk. So if you like,
the modular, right? Modular.
Yeah, absolutely. The fact that instantons have a location, if you like, yeah, the fact that they have moduli, very good. Yeah, so that's an equivalent way of saying it. Another way of saying it is that you cannot write the d bar operator for instanton in Twistor space. You cannot write it in this form that's in a box here. It doesn't take that form. Take some other form, it will still square to 0. It cannot be written in this form. This expression that's in the box here, this is key to us being able to do everything that I told you about today. Now, it doesn't mean that you can't figure out some other way of doing it. And this is something we're thinking about for an instanton. It just means you need some different machinery. Does that answer your question?
Yeah. Yes.
Okay.
Any other questions? Okay, I want to ask one thing concerning ADS. So, well, ADS is not chiral background, I guess. But
well, in some sense it is, right? Yeah.
Can you try, I don't know, to map somehow amplitudes in flat space to amplitudes in ADS? Maybe there is some kind of canonical map similar to these ones.
Yeah. So yeah, I know. Well, I know this is a topic kind of near to your heart. So yeah, this is something I've thought a lot about, and I have a partial answer to it. So as you well know, the kind of issue when you go to ADS is that the amplitudes, the ADS amplitudes in some sense, they receive boundary contributions, right? So unlike in an asymptotically flat setup, you can get contributions to the amplitude that don't have any bulk singularities. And what that makes it very difficult for this kind of formalism to capture those boundary contributions. So what you can do is find all multiplicity Twistor expressions which capture all of the bulk contributions to an ADS amplitude. So that is to say, everything that would be coming from contact vertex in the bulk of ADX, or anything that came from a bulk-to-bulk propagator. So you can find formulae that do that, but they don't have the boundary contributions to the amplitude. So in some sense, they're like some kind of integral kernel that captures everything about the ADS amplitude that would survive in some sense in a flat space limit. So it's something non-trivial, and it knows that it's in ADS. So you know, it's sensitive to the fact that you're not in Minkowski space anymore, but it's not strictly speaking equal to the ADS amplitude. And I guess one way of seeing that is that it won't obey conformal ward identities the way that it should in ADS. Okay, so that's one answer. But using this other formalism that I sort of vaguely referenced earlier, this kind of ambi-Twistor formalism, people are trying to find ways to get the whole ADS amplitude using ambi-twistor formalism. So there were some papers earlier this year, maybe 2 or 3 months ago, by Rurig and Skinner and by Eberhardt, Komatsu, and Misera that did this for scalars. Okay, did this. I think those people would be the first to admit that those formulae are not quite there. They're not what you're actually after. They present the ADS amplitude as a sum over Witten diagrams, essentially, which, okay, I mean, that's what we think of ADS amplitudes as anyway. So they present that sum in a compact way, but it's not really, I think, what one should be hoping for yet. But it shows that some progress can be made. Sorry, it's a bit of a long-winded answer, but that's what I have to say, I guess.
And okay, so the last question from me. So what about higher even D, higher dimensions?
Okay, yeah. So that's another great question. So again, there in higher dimensions, you really want to be trying to use this ambi-twistor formalism, and the reason for that is that twistor theory remains a chiral formalism, even in higher dimensions. And the problem is that in higher dimensions, there are no interesting chiral configurations for Yang-Mills theory or for gravity, for instance. So that means that the only interesting backgrounds you can describe in 6D, for instance, with twistor theory are flat ones. Whereas for ambi-twistor theory, that's not the case. That is kind of a dimension agnostic formalism. So for instance, the Eberhardt Komatsu Misera paper for ADS, that's in any number of dimensions. Okay, for biojoint scalar in any number of dimensions. It's up to you how interesting you think such a theory is, but yeah, that formalism is more dimension agnostic. But twistor theory, it really it's really beyond 4 dimensions. For spin 1 and spin 2, it's very difficult to do anything that isn't conformally flat, basically. Yeah.
Mm-hmm. Thank you. No any other questions? Okay, if no, then thank you very much for a good talk.
It's a pleasure. I'm sorry I had to run away a couple times there. It's my fault.
Problem. And see you next time, everyone. Okay, goodbye.
Sorry, I'll stop sharing here.
Okay, thanks, Tim. Yeah, thank you.
No, a pleasure. Like again, I'm sorry I had to kind of run to and fro while that was happening.
Thank you. Goodbye.
Okay. Yeah. See you next time.
Yeah. Yep.